Well, welcome back, everybody. All right, couple of comments just to make sure we're all on the same boat. Remember, we have the next exam today. It opened up today at 7 a.m. It will close up tonight, so don't forget to do it. Give yourself plenty of time. Okay, I believe it's 11:49 or 59, I should say. So don't wait till 11:58. Okay. All right. A couple of questions about chapter, the acid and base chapter, and I want to share a couple of things with you. I also been looking at the beakers for the activity, and I want to go over some of those aspects. Okay, so let me get back to that chapter, and then we'll continue with the rest of chapter 10. Okay, now remember we talked about two types or two definitions of acids and bases. Okay, now an acid, be it either this definition Arrhenius or be it the Brownstein-Lowry, okay, an acid produces a proton, and that is that hydrogen that has lost its electron, resulting in a positive charge ion. Refresh your memory. Hydrogen is in group one, like everybody else in that group. They have one valence electron. Hydrogen is not a metal. Remember that part too. It just happens to be in that group because it has one valence electron, which we'll lose. Okay. And theoretically, well, it can also be in group seven. Okay. Because in group seven, that's where the halogens are. It hydrogen can pick up one electron because that 1s1 orbital is empty, is minus one electron. So there's room for one more. Okay, so it's very unique of hydrogen to be able to do that, to both act as a cation and act as an anion. You may see it someplace, somewhere where you got hydrogen acting as an anion. We call that the hydride. When it's a cation, it's a positive charge, we call that a proton. So the Arrhenius definition is any moiety, any chemical compound that when put in an aqueous solution, okay, meaning a water solution, it will dissociate to produce the proton and the corresponding anion, whatever the anion will be. Now, an acid is a covalently bonded molecule. It is. Hydrogen's a nonmetal, okay? Chloride's a nonmetal, but that is the only example of a covalent bonded compound that in solution, in an aqueous solution, dissociates, okay? We had talked about ionic compounds. Those are fully charged positive, fully charged negatives, and they just a metal, non-metal. They dissociate in aqueous solutions. Now they dissociate 100%. Some of them do. Some of them not as much. It's a factor of solubility. Okay, so back to the definition. Arrhenius acid is any chemical which will be a covalent bonded acid that produces a proton is defined as an acid, Arrhenius acid. Now, with respect to bases and Arrhenius definition, is anything that produces in aqueous solution this polyatomic ion, that is the hydroxide. And notice with the starting material, sodium hydroxide, it's an ionic compound. So there are I can't think of one off the top of my head, of covalently bonded hydroxide producing bases. So you'll find the bases all to, in, at least at Chem 130, all of them to be inorganic compounds, okay? Now, with respect to the other definition, the Brownstein-Lowry, you see the Arrhenius deals specifically with the hydroxide polyatomic ion. And it kind of limited the definition because there are compounds out there that are basic in nature, but have nothing to do with the hydroxide. Okay. And let me clear this up a little bit. Okay, got a question. Yes, that is. I was going to mention that. Okay, but let me get to that part. Question was, do we get a second chance of the activity as far as making beakers? And my response is yes. But let me go over some aspects about that, and then we'll get more into it. And you can just go back in and resubmit it. Not a problem. All right. Now, with respect to, um, uh, well, we entered the neutralization reaction. Okay, that's just simply a reaction of an acid and a base. We talked about that. Now let's talk about the Bronsted-Lowry definition. Okay. Now in both cases, the Arrhenius definition and the Bronsted-Lowry definition, they're similar with respect to uh, um, an acid, because in both cases they produce. The Bronsted-Lowry says it loses the proton, and the Arrhenius definition says it creates or forms a proton. Either way, you're making a proton. So they're similar in that in both definitions, they produce a proton. So it is defined as an acid. Where they differ is their definition of a base. Okay. Now, with respect to Bronsted-Lowry definition, a base is any compound, any chemical that will accept that proton. Okay, that will accept it. Now, if we go back to the neutralization reaction, aren't we doing that anyway? This encompasses hydrogen chloride produces a proton. Make sure I mark it right. Here's our proton coming from hydrogen chloride or hydrochloric acid, and then sodium hydroxide producing the proton. Isn't the hydroxide accepting the proton to make water? Okay. And even though we define it as an Arrhenius, the Bronsted-Lowry also takes into account that the hydroxides come into play. So it expanded the definition of an acid of a base and bases. And if you go back to the Bronsted-Lowry, here you see that ammonia, NH3, has nothing to do with hydroxide here. But refresh your memory on the Lewis dot structure of ammonia. Yeah, it had a lone pair in the central atom. And what's happening, the proton comes in with its empty orbital. Remember, it has a plus charge, but that 1s orbital is still there. And so that lone pair actually on the nitrogen actually inserts into the orbital of the hydrogen of the proton to generate this ammonium chloride. Okay. And so in this case, ammonia is a Bronsted-Lowry base because it accepted that proton. Okay. Just like the hydroxide did. The hydroxide also accepted it to make water. However, here it didn't make water, it made the ammonium chloride. It did neutralize the acid just like the hydroxide did. Okay. So one way, if you ever have a odor of ammonia, I think we all smelled it. If you add a little acetic acid, a little vinegar to it, it will form the salt, the ammonium acetate, which is not as volatile, help to get rid of that ammonia odor. Yeah. Little side note there, little chemistry in real life action. Okay, so I hope that answers the difference between the Bronsted-Lowry acid and the Bronsted and the Arrhenius acid and base. Okay, all right, good. All right, well, let's talk about very quickly about those diagrams, and which is the end here. The one page that will kind of summarize all this for you. Let me find it. I was there first. Give me a second. Oh yeah, quick comment. Um, if one of the homeworks, you may have been, I think in chapter 9, you may have been asked a question of whether the pH 2 is weakly acidic or strongly acidic. Well, normally it's considered to be a strong acid. However, your diagram, if you look at it, 2 is in the weakly acidic domain. Okay, well, that scale should be moved over, but it's not. The correct answer is strongly acidic, but if you wrote that, if you selected that or count you wrong, let me know. I've since corrected the answer to fit with the diagram. But if I forget the number, what number question that was. I want to say number 7 or 8, possibly. Check it, and if it's wrong, shoot me an email and I'll correct it for you. Okay. But technically, a pH of 2 is really considered a strong acid. Okay. All right. And the same is true with pH of 11 and 12, considered a strong base. But like I said, that diagram's a little bit off. I think something got lost in the transfer of images. Okay, where was I? Let's go back, and we have one diagram. We talked about that. Let me go to that file. That will summarize everything, and I'll get to it. Give me a second. Okay. All right. What compounds belong in each? So, what is considered a strong electrolyte? Okay, that is a strong acid, strong base, or any soluble ionic compound. Okay, and soluble meaning using the solubility table to define whether an ionic compound is soluble. So what this means is this: being a strong electrolyte, which is a strong acid or strong base, when you write them as ions, they're 100% dissociated. Okay, 100% dissociated. If it's a strong acid, then you know you're going to have H something. So you're going to have a lot of protons in solution. And nothing will be recombined. You have a strong base like sodium hydroxide, be totally all sodium ions and hydroxide ions. Okay, or any soluble ionic compound, strong electrolyte, they'll be totally dissociated, like sodium sulfate. If you look at the solubility rules, anything with those top 4 cations, totally soluble. Okay. Now, weak electrolytes, that's a weak acid. We gave you a list of weak acids and gave you some examples of weak bases. And anything that is insoluble based on the ionic compound solubility rules. Okay. And so when you draw these is when you have a weak acid, okay, you're going to have some of the material, they're liquid form, but they stay together. I'll go back to the slide here in a second. And some maybe 1, maybe 2 sets of ions in solution, at the minimum, at least 1 set of ions in solution to demonstrate that it is weak. And then anything that's insoluble, again, similar thing, we're going to have maybe 1 set of ions in solution, and then the bulk of the ion will be in the bottom of the container, as trying to show that it's still combined and it's insoluble, therefore we have a solid. Okay. Now a non-electrolyte, which would be like sugar or carbon dioxide, okay, they don't dissociate. Remember, covalent compounds in an aqueous solution do not dissociate with except one exception, and those are the acids, okay? Hydrochloric acid, hydrobromic acid, nitric acid. Those are the only examples of covalent compounds that dissociate. That means all the other covalent compounds, whatever they may be, they stay intact in solution. They don't break apart through the oxygen. So carbon dioxide, if I put that in water, it's still carbon dioxide. It doesn't mean that oxygen comes off and it's floating around in water. It doesn't mean that at all. It's still combined as carbon dioxide. Okay. And so let's go back to the, yeah, right here. Now, nitric acid, we went through this, is a strong acid, is one on the list that we put down as a strong acid. Being a strong acid, based on the slide we talked about, it's a strong electrolyte. Being a strong electrolyte means that all the ions are in solution with their charges. So don't forget to put their charges. So we got protons floating in solution, and we have, in this case, the nitrate ion floating in solution. Okay. It's not necessary to put water molecules in there. If you want, that's okay, but it's not necessary. But that first beaker diagram demonstrates how to display a strong electrolyte, be it a strong acid, strong base, or a soluble ionic compound. Now, HF was a weak acid, okay? A weak acid. And so to show that in the diagram, we need at least one pair of ions, okay? And that is denoted by these right here, the proton and the fluoride, just one pair. Don't forget the charges. The rest of them at least showed, 3 to 5 combined molecules of HF in solution. Notice that they're together, okay? Because this is a weak electrolyte. There's very few ions in solution. The bulk of the compound is still together and not dissociated. And that's denoted by HF, still combined. So let's show about 2 or 3 of them, okay? The next example, potassium hydroxide. We may look at it and say, well, okay, we got potassium, we got hydroxide. I have an ionic compound. Oh, that tells me use the solubility rules. Well, using the solubility rules, I go down to the table and look at number 1. So lithium, sodium, potassium, ammonium, always 100% soluble, which tells you I got a strong electrolyte, which tells you all of the ions that I put there, which would be the potassium and the hydroxide, will be written as ions. Now, the hydroxide does not break apart. You don't get oxygen and more protons, okay? Remember, the hydroxide is part of the polyatomic ions from the polyatomic ion table. If those go in solution, they stay together with their respective charge. You could have the sulfate, the SO4 -2 ion in there, or the sulfite ion, or the nitrate ion, or the nitrite. None of those break apart. They stay together as a packet. But you show them together with their respective ions and their charge. Okay. Last example is the magnesium hydroxide. Okay. Well, we look at the formula. First thing we figure, it's not covalent, right? Because we got magnesium there. So the only one thing I have is ionic. All right. So that means I need to use a solubility table to determine whether it's soluble or insoluble. So going to the solubility table, I look for the hydroxide, which is in the second column in the insoluble column, and that's number 10 in that table there. It tells me that the hydroxide ion normally is insoluble unless it is bonded with the big 4 in number 1, or bonded with calcium, barium, or strontium. And so all hydroxides in the world, with the exception of 7 examples, are insoluble. Okay, those 4. So if I had lithium hydroxide, sodium hydroxide, potassium hydroxide, ammonium hydroxide, calcium hydroxide, strontium hydroxide, or barium hydroxide, those guys would be soluble, which means they'd be strong electrolytes, and I would show them like the potassium hydroxide example. But magnesium is not part of that, of those 7, therefore it is insoluble. Okay, And so I still need to show some ions in solution, at least one set. And I got one set of ions, magnesium with a +2 charge. How do we know that? Magnesium's in the group 2, it's 2 valence electrons. When it becomes ionic, it will be a +2. And why are there 2 hydroxides? Well, in the formula it was Mg parentheses 2, which tells you that I have 2 hydroxides because each one is a -1, and I need to balance a +2 of the magnesium ion, so I require 2 of them. And so by analogy, it's like taking a bicycle, two-wheel bicycle, taking the tires off. Magnesium +2 represents the frame, and the hydroxide represents the 2 tires that you have removed. Okay? And so do show, now again, like the hydroxide and potassium hydroxide, it's a polyatomic ion. They do not, the hydroxide, the oxygen and the hydrogen of hydroxide do not break apart. They stay in one unit called the hydroxide. Okay? So that's basically it. And if you notice down at the bottom of the beaker, you have the magnesium hydroxide, and this little line that represents that it is insoluble, and therefore if I were to put some in solution, it would crumble out and just settle to the bottom. You've seen this before. If you ever use milk or magnesia, you have to you let that bottle, you pour some out in a clear glass, it will separate. Milk or magnesia is basically magnesium hydroxide plus some other components. And what do? You got to shake that bottle up so you can, mix it up well. It won't really go in solution. It just makes an emulsion. But as it sits there, it settles out. And that big clump of magnesium hydroxide is in the bottom of the container. Okay? Not combined in solution like HF, because HF is a liquid. Okay? All right. Magnesium hydroxide is a solid, and it will fall to the bottom of the beaker. Okay, so with that being said, you're more than welcome to go back and resubmit your beaker drawings, okay? And look, if you're happy with what you submitted, that's fine. I'll go with that and I'll grade it, but I will look at them again. So you do submit it. If I did grade it, shoot me an email and I will open it up so you can resubmit it. But you should be able to resubmit it anyway, whether I graded it or not. Just send me an email that, or a message within the assignment that you resubmitted your file. Okay. Any questions about any other things with respect to these chapter 7, 8, and 9 for today's exam? No? Okay. Well, let us continue then with reactions. This is where we ended up on page 14 of chapter 10. Chapter 10 deals with chemical reactions. We were going with showing specific examples. Let me back it up. We had 6 types of... Yes, go ahead.
It looks like Dusty asked a question in the chat. He asked how many questions per chapter for the exam.
Oh, that's a good question. I'll have to find out. I'm not sure. This one, I don't have the privilege of making this exam. These exams have been made by other professors. I didn't make the first exam. Other professors, I made the other exam. So I want to guess it's about 30 questions, very similar to the last one. I couldn't tell you how many per chapter, but I suspect there should be at least maybe two or three. But let me find out, and I'll shoot a general email to everybody. Okay? Well, I could have said there's 100 questions per chapter. How's that? I'm just kidding.
No, I think I took the test this morning, and it's 32 questions, but it's kind of average per each chapter.
Average?
Yeah, yeah, it's like,
About 2 or 3?
I, I don't know. There, yeah,
I would take, yeah, I would probably think about 2 to 3. That's what we all try to do when we created the exams. Okay. All right. Well, I'll find out, be more specific. Okay. So we're talking about chemical reactions. All the chemical reactions that occur in chemistry, basically just 6 of them. I'm gonna go back to them very quickly. We have a combination reaction, and just by the definition of the name, that's what it does. You take two elements, 9 times out of 10, you're dealing with elements, and you put them together, okay, to to create a compound. Because remember, by definition, a compound is when two different elements come together. At the minimum, two different elements come together. All right. So the opposite of a combination reaction would be the decomposition. So you have a compound, in this case ABC, and you do something to it, heat, electricity, any number of things, and you break it down to the respective elements again. A good example, you got a question here. Is this test on more than 3 chapters? No, 7, 8, 9. Okay. All right. Decomposition reaction, we break it down. Combustion reaction, basically just what it means. One of the principal reactants for any combustion, obviously, is oxygen. So you notice that oxygen is a reactant. The products, the only two products that you're going to get for this type of combustion reaction are simply carbon dioxide and water. That's it. Now, what is being combusted? Well, there's a variety of different things that be combusted, but for us here at Chem 130, you're going to simply see what we call a hydrocarbon. Okay, a hydrocarbon is a compound that is made up of nothing but carbon and hydrogen. So a good example would be fuel, gasoline, propane, butane. Those are some examples that what we're going to be using as far as combustion reaction. Okay, that subscript X and the subscript Y are numbers of how many carbons we have. The minimum X is 1, and the minimum Y is 4. And that's the smallest hydrocarbon, which is methane. Okay, so point about that, oxygen's required. The only two products is carbon dioxide and water. And yes, we understand that when you combust your fuel, you get carbon monoxide. Fully understand that. That has to do with the efficiency or lack thereof efficiency of our engines that don't combust correctly to, to convert all of the hydrocarbon into carbon dioxide. All right. So, and then the other type is an acid base. We talked at length about acids and bases, where a proton, generally written with H first, followed by A, whatever A may be, could be nitric acid, could be the chloride, could be any covalent compound, but it's an acid that produces a proton reacting with a metal hydroxide, okay? And the hydroxide in the water, we get, the only product you get is water. The proton and the hydroxide always give you water, okay? So water is one of my products, and what is left is the salt, what we call the salt. So the metal of the hydroxide, okay, which is the cation, combines with the anion of the acid here, which is defined as A, shown as A. And so we make M, which is a metal, and A, which is the anion. So, okay. Then we have what's called a single replacement reaction. Now, you'd be familiar with the periodic table. If you're not, by now, hopefully you get to, because I refer to it quite a bit. Okay. So in the periodic table, right above the solubility rules, we have what's called the activity series. And what this is, lists a certain amount of metals, not all of them, that list their relative reactivity. So lithium is the most reactive metal in this group. In fact, those metals that are underscored and are in bold print, those are extremely reactive. That means that if I just put them in water, they react quickly and rapidly without any other type of need to get it to go into reaction. The other guys take a little bit of more conditions, more like an acid solution to get those to react. And then at the end, you have Au, which is gold. That is the least reactive metal. Doesn't mean it doesn't react. It just means it's very inert. We can get gold to react, but it takes very vigorous conditions. Okay. um, that's why I explained that gold, that's been buried for thousands of years. You take it out, it's still as shiny as the day it was made because it's very unreactive. And so be familiar with the activity series because we're going to use that to determine if a reaction is going to proceed. Okay. And we have a very simple step process to determine whether that's going to happen or not. Okay. We'll get to it. We'll explain that. Then what we have is called a double replacement reaction. Now analyze the reactants. We got M1X reacting with M2Y. And then look at the products. Now we have M1Y. So in essence, what has happened is the partners, the anions have exchanged. Okay. M1X, let me highlight that. Okay, now becomes M1Y. They just exchange the anions. And the same is true for M2Y. Okay, let me highlight that, change the color a little bit. Okay. Now, to determine whether a reaction proceeded, now point number one, the reactants M1X, M2Y are soluble in aqueous solutions. If you look them up in the solubility rules, totally soluble. The products depends, again, on the ions here. So what we do to determine whether a reaction proceeded, point number one, if the products based on the solubility rules are all soluble, nothing happened, no reaction occurred. Okay? But if we look up M1Y and we find it that the solubility rules tell us that it is insoluble, then a reaction proceeded. Okay, it becomes a solvent. And so the products, a reaction for this type, a positive reaction, is dependent on the solubility of the products. If both products are insoluble, no reaction. If both products are soluble, reaction proceeded, but you're going to have, if reaction proceeds, you're going to have at least one of the products to be insoluble. Therefore, you have a reaction. A positive reaction, I should state. Okay, so that's called a double replacement reaction. Single replacement reaction deals with activity series. Acid-base deals with that proton and hydroxide reacting. Combustion reaction just simply deals with burning the combustion with oxygen of some hydrocarbon. Okay, a decomposition reaction. You may have done this at home. Anybody know why you put sodium bicarb in chocolate chip cookies?
So that they rise.
As they rise, exactly. So that's a very good example of a decomposition reaction because the baking soda is heat sensitive, and when you put it in heat, it breaks down. And when it breaks down, one of the products is carbon dioxide, and so now you got a little fluffy cookies, okay, as compared to flat cookies. All right, so that's a good home example of a decomposition reaction. All right. So we went through examples here of a combination reaction. Notice that we have two elements reacting to form a compound. Okay, diphosphorus tetroxide. Okay? And of course, we balanced it. You got to make sure we balance things. That's a good example of combustion reaction. Here we have an example of decomposition reaction. This is iron 3 oxide, aka rust. We heat that up, pretty high temperature. We drive oxygen away and we create iron, pure iron. So one means to isolate iron. So if we can find this in space, we have an oxygen source here. So we can create oxygen. Again, we balance the chemical equation. Note the ratio. 2 iron 3 oxides produce 4 irons and 3 oxygens. Okay, that's our ratio. Every time we balance an equation, analyze the ratio. We're going to be using those one time. Combustion reaction. Okay, with respect to the first two examples, as far as balancing, those examples for what we do is we have basically a trial and error. Throw in a number, see if that works, move to reactant to products back and forth until you find a set of numbers that will balance that chemical reaction. Okay. Now, when you end up with a set of numbers, see if those numbers are divisible. In math terms, bring it to the lowest common denominator. You bring it down to the lowest number. So you could end up with, say, four iron 3 oxides, 8 irons, and 6 oxygens. Okay, it's balanced, but bring it down to the lowest common number, in this case, 2, 4, and 3. Okay, so basically those first two types are kind of a trial and error. Throw in the number, see what happens. We don't have, it's more specific when it comes to combustion reactions as far as balancing. So here we have propane gas. So, this past weekend you were doing a cookout, that's what you were burning. Propane gas has 3 carbons and 8 hydrogens. You need oxygens. Without oxygen, you can't burn anything. And the products you always get, at least for Chem 130, is carbon dioxide and water. Now, to balance these stepwise, we balance the carbons first. So number 1, balance the carbons. Okay. Number 2, balance the hydrogens. And then number 3, the last one, balance the oxygen. Okay. So that for combustion reactions, for hydrocarbons, you follow that format, you'll get your balanced chemical reaction. So in this case here, we have 3 carbons in the far left and only 1 carbon as a product. So if we put a 3 in front of carbon dioxide, that balances our carbons. Okay. Now, next thing, look at the hydrogens. We got 8 hydrogens on the reactant side, but only 2 in the form of water. So if we put a 4 in front of water, that balances out the oxygens. Now we look at the oxygens. So if we put a 4 in front of water, that gives us 4 oxygens. Okay, and then we had a 3 in front of carbon dioxide, which gives us 6 oxygens. So we have a total of 10 oxygens. So that means the last thing to balance is the oxygen. I could just stick a 5 in front of oxygen O2 and we're balanced. Okay, and you end up with this. So 1 propane requires 5 molecules of oxygen to produce 3 molecules of carbon dioxide and 4 molecules of water. And it's a gas. Somebody asked me a question, why is it a gas? Why is water a gas? Well, we're burning it. Okay, it's heat, it's hot, so it's going to be water vapor going into the air. Okay, and so you can see where a good source of one of the pollutants in our atmosphere is carbon dioxide coming from the burning of hydrocarbons. Okay. All right. Now, just let me clear this up a little bit. This is basically what I just told you about balancing. Okay, hydrocarbons, simple hydrocarbons. You do the carbons first, followed by the hydrogens, followed by the oxygens. Okay, and you always end up with a balanced chemical reaction. Acid-base reactions. Here we have an acid and a base, in this case, a metal base, all right? Always gives us water and then the corresponding salt. Now, when we balance acid-base reactions, follow the proton, follow the hydroxide. If you follow those, you're going to be in good shape. And so if you look at this reaction, the first one, we got hydrochloric acid, so it's got one proton, okay? And we got barium hydroxide. It's got two hydroxides. Now remember, one proton per one hydroxide give me one water. So if I have two hydroxides, how many protons do I need? Anybody want to take a number? If I have two hydroxides, how many protons do I need to neutralize those two hydroxides?
Would it be too low?
You need two, okay? I need two hydroxides to balance out the, two protons to balance out the hydroxides. So I could just simply put a 2 in front of hydrochloric acid, and that would balance out my hydroxides, which means how many waters would I get? Okay, everybody agreed that we need two hydroxides, right? Two protons to balance out the two hydroxides. So how much water would I get? H2O. How many molecules of water would I get if I have two protons and two hydroxides?
Would it be one?
Think about it. If one hydroxide, look at the first reaction. One hydroxide requires one proton to give me one molecule of water. Okay? So the ratio is 1 to 1, right? If I have two hydroxides, I need two protons. How many waters am I going to make?
Two.
Exactly. I'm going to make two waters. So I'm following to balance these. I'm following the water. Now, the chloride. Remember, if you look at the general reaction, the A in the general reaction is, in this case, the chloride. So we got to break that down before we can put them together, break them into the ions. Let me put a plus there, they get separated. So I got chloride is one of the ions I'm going to make, right? What about the barium? What is the charge in the barium? Ionic barium. What group is barium in? Well, even if you didn't know what group, the hydroxides are all -1, right? I got two of them. What must be the charge on the barium ion?
+2.
Got it. It has to be +2. Okay. Verify that. Barium is in group 2. Okay. It's going to have 2 valence electrons. And so now, before I can put the barium and chloride together, I need to make sure I put enough of each to make the right formula. So I need 2 chlorides for every barium. Okay. And so I can write down, I'm making 2 waters because I got 2 hydroxides and I have 2 protons. Okay. Now I got 2 chlorides, which by the way, the chlorides get balanced, and 1 barium, which by the way, the barium gets balanced just by default. Okay. And so am I not balanced here? I certainly am. I forego the blue 2, that's the 2 I put in there. But the yellow 2, I got 2 protons there, 2 hydrogens from hydrochloric acid, I got two coming from a hydroxide of barium hydroxide. Barium hydroxide. That's a total of 4 hydrogens on the reactant side. On the product side, I got 2 molecules of H2O. That's 4 hydrogens. So my hydrogens are balanced. Okay. Look at the chlorides. I got 2 chlorides from hydrochloric acid as reactants. I got 2 chlorides in the form of barium chloride. So the chlorides are balanced. What's left now is oxygens. I have 2 oxygens in barium hydroxide, and now I got 2 oxygens in the form of water, H2O. So the oxygens are balanced. I got 1 barium and as a reactant, 1 barium as a product. And so I have a balanced chemical reaction, which means that, let me clear that up so we don't confuse it. That means that for every barium hydroxide molecule that I react to neutralize, I need 2 molecules of hydrochloric acid, which will give me 2 molecules of water and 1 molecule of barium chloride. Okay? So the ratio between HCl and barium hydroxide is a 2-to-1 ratio. Okay, so if for example, think about this for a second. What if I had, yeah, 8 molecules of hydrochloric acid? Okay, how many how many molecules of barium hydroxide would I need? Okay, you had 8 HCl's. How many barium hydroxides would you need to make sure that the 8 hydrochloric acids get neutralized?
Would it be 4?
Got it. Exactly. It would be exactly 4. I would need 4 barium hydroxides for every 8 because my ratio is still 2-to-1. Isn't 8 to 4? Isn't that a 2-to-1 ratio? Yeah. Okay. This is how we use that stoichiometric. We're going to call it stoichiometric relationship. That is the ratio between the reactants and products. And if I had 8 molecules of hydrochloric acid, 4 molecules of barium hydroxide, how much water am I going to make? How many molecules of water am I going to make?
Eight.
Exactly. I got 8. I will make 8 molecules of water based on my ratio of, look at my ratio in yellow, 2 hydrochloric acids to 2 waters, 2 to 2, it's a 1-to-1. So if I have 8 of HCl, I'm going to make 8 waters. Okay. If I have 8 HCl, how much barium chloride am I going to make? Starting with 8 HCl's. Anybody want to take a educated guess on this? No need to guess. You got the answer right in front of you. If I start off with 8 HCl, how much barium chloride am I going to make? If I got 8 HCl, 4 barium hydroxide, it's going to make
4.
me, exactly, it's going to make 4 barium chloride because my ratio is 2-to-1. Okay, it was 1/2 of my HCl. Okay, so this is a classic example of the type of problems we're going to be doing later on. Right now, I'm saying molecules, but eventually I'm going to change those numbers to grams. Okay, how many grams of barium chloride I'm going to make if I start off with 8 grams of hydrochloric acid. And we're going to have to depend on the balanced chemical equation. Otherwise, our numbers will be incorrect. That relationship, that balanced chemical reaction, is true whether I do it in the lab scale, in gram scale, or if I put everything together and make a plant, big industrial plant where I'm making tons of this material. same ratio comes to play, regardless of how big of quantities I'm using. Okay, now here's another one for you. Let's clear this out. Oh. Okay, acid-base reaction. How do I know that? Well, I got, like I said, 9 times out of 10, you got hydrogen written first, and then this you should know, you should recognize by now the hydroxide. Okay, so I have an acid-base reaction going on. All right, so when we try to balance it, what is the one thing I'm going to make all the time? Water, right? I'm going to make water every time a proton and I make hydroxide react to 2. Okay, so follow the protons and hydroxides. How can I make the protons and hydroxides balanced here? Because I got 2 hydroxides from calcium hydroxide and I got 3 protons from phosphoric acid. How can I balance those 2? What do I need? Remember how we were putting +2 and a +3 charge together to make a formula? Can't we use the same principle here? How can I balance out 2 hydroxides and 3 protons? What would be the common factor? What's the common factor between 3 and 2?
6.
6, right? So what if I were to, put, let's say, a 3 there? Wouldn't that give me 6 hydroxides, right? And what if I put a 2 in front of phosphoric acid? Wouldn't that give me 6 protons? Okay. Well, if I have 6 hydroxides and 6 protons, can anybody tell me how much water am I going to make? How many waters am I going to make? If I have 6 protons, 6 hydroxides, how many waters am I going to make?
Is it 2?
0? How many?
2?
2? Oh, okay, let's think about it. Okay, let's think of an analogy. Think of the hydroxide, think of the protons as
Oh, 3.
the frame of a unicycle. So if I got 6 unicycles and 6 tires, how many assembled unicycles am I going to make?
6.
6, right? Okay, now go back to it. The hydroxide represent the tires. I got 6 of them. The protons represent the bicycle frames. I got 6 of them. How many waters am I going to make? How about 6? Would you guys agree or disagree? You get 6. Okay? Because the hydroxides, again, think of it as, I use analogy as the unicycle, 2-wheel bike and 3-wheel bike. The hydroxides represent the tires. I got 6 tires. The protons represent the bicycle frame of a unicycle, 1-wheel tire, bicycle, right? So if I got 6 frames and I got 6 tires and I'm going to assemble them, I'm going to make 6 assembled unicycles, right? The same scenario. If I got 6 protons and I got 6 hydroxides, I'm going to make 6 waters. It's a 1-to-1 relationship. Okay. All right. So what about the anions? Well, break it down. We're going to make the phosphate, the PO4. Okay, those 6 protons are going to get reacted. So we're going to make the PO4, which is a -3. Oops. That's the phosphate ion. And then we're going to make the calcium, which we know will have a +2 charge. Okay. So now I got to put calcium and phosphate together. Guess what we have here again? We have another -3 and a +2 combination, right? And so I need a common factor like we've been doing. So I need 2 of the phosphates and 3 of the calciums to write that formula down. Okay. Put this over here. And so I end up, got a 2 there. I got a 3 there because I wanted to balance out the hydroxides and the protons, which gives me 6 waters. And then I broke down the salt as ions. Okay, because calcium has a +2. I need 3 of those to balance out the total -6 of the phosphate, which means I need 2 of the phosphates. So my formula is calcium, subscript 3, parentheses, phosphate, subscript 2, calcium phosphate, plus 6 molecules of water. And by default, the salts balance out. By balancing, when you talk about acid-base reactions, to balance them, follow the protons and the hydroxides, and the corresponding salts will fall in place. Okay, was what we did up here. Let me here a little bit. Okay, go back and check. Are we balanced? Well, we have 6 hydrogens coming from phosphoric acid, and we have, how many hydrogens come from calcium hydroxide? 2, right? But there's 3 molecules of calcium hydroxide. So we have 6 total hydrogens coming from calcium hydroxide. So we have a total of 12 hydrogens, 6 from phosphoric acid and 6 from calcium hydroxide. And we have 12 hydrogens in the form of water because we created 6 molecules of water. Okay. We got 3 calcium reactant side, 3 calcium in the product side. The phosphate, we got 2 phosphates in the reactant side. So we got 2 in front of phosphoric acid, that's 2 PO4s. And in the formula, we have 2 PO4s. Okay, so we are balanced. We got a balanced chemical reaction. Okay, now let me ask you a question. If I have 4 phosphoric acids, can somebody tell me how many calciums do I need? Oh, whoa, I messed up my, where'd it go? Okay, there I am. I got lost here. Everybody see the file? If I have 4 phosphoric acids, can you tell me how many calcium hydroxides do I need?
6.
Okay, 6. Yeah, exactly. I need 6 of them because my ratio is 2 to 3. Okay, so my ratio of whatever I start off, if I'm given 4, then I'm going to need 6 calcium hydroxide. That's still the same ratio, 3 to 2. Okay, and we're gonna be doing things like this down the road, but I'll show you another technique when we get to it. I was hoping you can recognize that ratio up front, and I see some of you have, but the others you can always set that up as a ratio and follow your units. cancel things out. All right, clear as mud. No? Okay. All right, single replacement reaction. That is when we get a metal, replaces a cation in an ionic compound. Okay. Notice we have some elemental metal, M, that will replace the A, which is a color here, in this ionic compound. The A is in some ionic form. And if reaction proceeds, that M will replace the A, okay, generating elemental A. I'm trying to keep it all color coordinated here. Okay. A classic example of this is plating. Some of you may have jewelry that's gold plated. The way they did that is they took a metal ionic compound, and most of the time they plate copper first, so it's solid copper, and you're able to replace that ionic gold into solid gold, plated gold on the surface. Okay, that's a classic example of what's called a single replacement reaction. Okay, and we utilize the activity series. Now, what we do is when we look at a reaction, we first compare from the reactant side the metals. We ask the question, which metal right here, M or A, is more reactive, regardless of what form they're in. Okay? That's the first question you ask. Which metal is most reactive? Then the second question you ask yourself is the most reactive metal in ionic form? If the answer is yes, then no further reaction, no reaction occurs. If the answer is no, reaction proceeds. You switch the reactants, okay? So first question, which metal is most reactive based on the activity series on the periodic table? Second question, is the most reactive metal in ionic form? If you answer yes, it's an ionic form already, then no reaction proceeds. If you answer no, reaction proceeds, okay? And we'll do some more examples here in a bit. But that's basically the questions you ask yourself, okay? And this is the activity series. In this case, the white ones are, like I stated, in your periodic table, they're underscored or they're highlighted. Those are the most reactive metals. This is telling you that lithium is a lot more reactive than gold. Gold is the last one. Now we utilize hydrogen. So H in parentheses represents hydrogen gas. Okay. Now, and so this is relative. This is a relative scale relative to hydrogen gas. Now, obviously the elemental form of hydrogen is H2. The ionic form of hydrogen can be water. Okay. The metals have their own ionic form depending on the charge. So lithium would be a +1, obviously, and so forth. So if we react with sodium, for example, if we look at sodium in the presence of water, okay, and let me write that reaction to demonstrate how that works with respect to hydrogen. If we wrote a reaction and say sodium plus water, question is, does that reaction proceed? Okay. Well, we look at the activity series, we find sodium, and then we know that the H2O is the salt form of hydrogen. So we find hydrogen, which is in parentheses in the activity series, And we see that sodium is a lot more reactive than hydrogen. And so the question then says, ask, you see that sodium is a lot more reactive. So the next question is sodium in salt form? And the answer is no. So guess what? You get a reaction that proceeds. And so you actually create hydrogen gas. In this case, we create sodium hydroxide. Okay? A hydrogen gas is created because the most reactive metal here is sodium. Okay? Now, if we were to compare, let's say, iron, pure iron in the presence of zinc chloride. Yeah, we know zinc chloride is +2, so the formula for zinc chloride is ZnCl2. Okay? Now, who can tell me if this reaction proceeds? You have a 50-50 chance here. It's either yes or no. Okay? Ask yourself the first question. Which metal is more reactive, iron or zinc? What is the answer there?
Is it the zinc?
Zinc is more reactive, exactly, because you see zinc is a lot more reactive than iron. That scale wraps around, so Cn wraps around to iron. So so zinc is more reactive. Second question, is the most reactive metal in ionic form? Would that be a yes or a no? We all agree that zinc is more reactive. That's correct. Now the second question is the most reactive, is zinc in ionic form, the way it's written? Yes, it's zinc chloride. Okay, it's not zinc metal, it's just zinc chloride. And so here we have Nr, which means no reaction. Okay, so what does that mean? That means that the reverse would happen. So reverse it. What if we had, let's just use for argument's sake, iron 2 chloride reacting with zinc metal. Oh, not A metal, zinc metal. Question is, would that reaction proceed? Okay, ask the same questions. Compare iron with zinc. Which is more reactive, zinc or iron? We already established that with the first example. We said that zinc is more reactive. Okay, so second question, is the most reactive metal in ionic form? Answer to that is no. Zinc is in elemental form. That means reaction proceeds. And so we replace the metals. Oh, okay. So we created, by taking zinc, pure zinc, and reacting it with iron 2 chloride, we get elemental iron. We plate iron and zinc chloride. Okay. In the first example that I demonstrated, number 1 example and number 2 example. Okay. In the first example, we asked the same questions. I got a question here. It's probably 5 minutes. You got it. All right. So in the first example, in both example 1, example 2, we simply asked the question, which is the most reactive metal? And we used the activity series to tell us that zinc is more reactive than iron. Okay, we use the activity series. Okay, and so we're given the first question, number one. Well, that being the case, is the most reactive metal in ionic form? So is zinc in ionic form in number one? The answer is yes. It's already in stable form. Okay, it's they're not going to react because it's already in ionic form. So we get no reaction for example number one. Okay. For example number two, same thing. Zinc is still more reactive than iron. That hasn't changed. Second question is the most reactive metal in ionic form. And we look at we see that zinc is an elemental form. So no, it's not an ionic form. Therefore, reaction proceeds. And we end up making zinc chloride plus metal. Okay? You see how that activity series works? Okay. You just ask those simple questions and that would tell you whether a reaction as written will proceed or not. Okay. All right. So let me clear that up a little bit. All right. So at the activity series, here's the steps that I just laid out, which is more reactive. Okay. And then is the most reactive in ionic form. If it already in there, already in ionic form, and then it doesn't, it's in stable form already, as stable as you can get it. So no reaction proceeds. Hence we rewrite the letter NR, no reaction. If it's not, we just switch the partners. Okay. Then of course we make sure we put them together with the correct formula because of the respective charges. Okay. And then, of course, we add the states solid, liquid, gas, or aqueous. Okay. And then we balance it like we never forget to balance. We always balance equations. Take a look at this one here. Okay. We have zinc nitrate in the presence of sodium. The question is, do we get reaction? Okay. And so we go to the metals, regardless if they're elemental form or salt form, and we determine which metal is more reactive. So here we're comparing zinc versus sodium. And so let me highlight those so we know that we're on the same page. So now we're going to compare the activity of zinc and versus the activity of sodium. So we find them in the activity series, and we see sodium is right here, and here's zinc. And so obviously sodium is much more reactive than zinc. Okay. And then the question is, all right, is the most reactive metal in ionic form? Well, in this case, no, it's not. Sodium is an elemental form. Okay. So therefore, reaction proceeds. So we exchange partners and we end up making sodium nitrate and we generate zinc metal. Okay. And now we have to put in the states. Well, sodium nitrate, based on the solubility rules, anything, remember the big four? Anything with lithium, sodium was one of them, is soluble. So sodium nitrate is soluble. Okay. So it's aqueous solutions because we started off with zinc nitrate in an aqueous solution. And then zinc is a metal, so elemental zinc we know is solid. So we put in the states, and then what we do is simply follow the, if you follow the anions, you got to balance, because if we follow the nitrates, we start off with two nitrates as reactants. We create one nitrate. Well, we stick a 2 in front of sodium nitrate, and then we go back and balance the sodium, and by default, it balances out. So for these type of reactions, follow the anions to balance them out. Okay? So the reaction proceeds here. What that means that the reverse is no reaction. You could be given the reverse reaction. What do I mean by that? Well, let's reverse it. What if I had sodium nitrate plus zinc? Oh, not A, zinc. Question is, would that reaction proceed? Okay, and same steps. We already established that sodium is a lot more reactive than zinc. And then the second question is the most reactive metal in ionic form. And for the example I just gave you, yes, it's already in ionic form. It's in the form of sodium nitrate. That's ionic. That means that this reaction does not proceed. No reaction. Okay. All right. Oh, I went over time. Let me stop it here. Sorry about that. Page 20. Everything.